I want to remind you that you should only be watching this video if you have exhausted all other resources. Task 5, Question 3. In this round, the golfer hits the ball at an angle of 87 degrees. Determine the velocity of the hit that would result in a direct shot into the hole. So you may notice that this question is fairly different than the other ones. In this problem, we do not know the initial velocity that we want to hit the ball with. That's what we're trying to find, which actually makes this problem significantly more difficult than the others. But we do know some other information that is not currently listed. We know that we want to get a direct shot into the hole, which means the coordinates of the hole have to be on the path of our golf ball. So we know that the golf ball, whatever equation we come up to model it, will have the point 33.435, 0 on the graph. And again, we know that the starting height, h naught, is still equal to 12 feet. So let's start to write our model and see what we can do with it. As before, our x equation will be defined as the horizontal component of the initial velocity, which is simply v naught times the cosine of 87, the angle of the hit, times our time. And our y equation will be defined as the vertical motion model, negative 16 t squared, plus the vertical component of the initial velocity, v naught times the sine of 87 times time, plus 12, our initial height. But at this point, things get messy. X is unknown, v naught is unknown, and t is unknown, as is y. We have way too many unknown values. So what we want to try and do is eliminate the parameter. Eliminating the parameter, you may recall from our study of parametric equations, involves solving one of your parametric equations for the parameter and then substituting that into the other equation. In this instance, the easiest way to do this will be to solve our x equation for t by dividing both sides by v naught cosine 87. Therefore, t equals x over v naught cosine 87. We now have an expression for t in terms of x, and we can take that expression for t, and we can substitute that into our y equation anywhere we see a t. So we have two spots that we will be substituting into our y equation. As we start to make our substitution, notice that we will start by writing our y equation as we see it. Y equals negative 16, but then instead of writing t, we are writing this equivalent expression for t, x over v naught times cosine of 87. And that entire expression needs to be squared because the t was squared in the original y equation. Now we will add to that v naught times the sine of 87 times t. But again, instead of t, we're writing this expression, which is x divided by v naught times the cosine of 87. And then finally, finishing the y equation plus our constant 12. At this stage of things, we have accomplished what we set out to accomplish. We've eliminated the parameter. There's no longer a t in this equation. But this is a little messy, and we can simplify it a little bit more. Notice in our middle term, we have v naught over v naught, which will eliminate each other. V naught divided by v naught is simply 1. And we have sine of 87 divided by cosine of 87, which, if you recall your trigonometry, sine over cosine, if the angles are the same, is defined as the tangent function. So we can replace that as the tangent of 87. Then we still have our times x, and we still have our plus 12 constant term. So we now have the equation we're going to use, but we still have three unknowns, y, x, and v naught. But actually, we do know two values that we can substitute into this. We know that we're getting a direct shot into the hole, which means the graph has to go through the point 33.435, 0, which gives us an x value and a y value that we can substitute in to this equation. So let's go ahead and do so and see what happens. You can see my substitutions for x and y made in pink. Now we have a single equation with one single unknown value, v naught, which means we can solve and figure out what v naught is. Now again, there are always different ways you can go about solving an equation, but I think one of the easiest ways to solve an equation is to graph it. So what I'm going to do at this point is I'm going to go to my calculator. I'm going to graph this entire mess right here with x as my variable in place for v naught. If I type that in carefully and type it in correctly and graph it as y equals negative 16 times 33.435 over x with a cosine of 87 in the denominator as well, all that squared, plus tan of 87 times 33.435 plus 12. If I can manage to enter that in correctly, I can graph it and calculate the x-intercept, which will solve this equation for x for me. So let's do just that now. Remember that if you are in a TI-84, your calculator has the fraction feature, which allows you to enter fractions that look like fractions, which is pretty nice. So as I'm typing this, I'm going to start by typing my negative 16, and then I am going to open a parenthesis and then type alpha y equals, enter, which will give me a little fraction bar. I can then type my numerator, 33.435. I can go down to my denominator and type x times cosine of 87. Close that parenthesis, arrow over, close another parenthesis, and square that whole thing. Now I can add to that the tangent of 87, close my parenthesis, multiply that by 33.435, and then finally add 12 to that. Make sure you are in degree mode, and now let's go ahead and graph it. Let's go to our window first to make sure we'll get a good graph. Remember, our x values are now representing our initial velocities. So reasonable initial velocity, I'd say probably 0 up to, I don't know, 75 will probably do the trick. We could go up to 100 if we wanted to. I'll go up to 100 just for the sake of it. And then after I've hit my x min and my x max, I'm going to do a zoom fit. So zoom 0 to access the zoom fit feature. My calculator will think for a moment, and then hopefully it will give me a graph. And I got a graph that looks like that. You might look at that and be a little confused. You might not think it's giving you anything useful, but it actually is. Notice that it is a rational function since our variable x is in the denominator. So we have an asymptote, which is fine. But since I know I'm looking for an x-intercept, I can actually probably make this window better myself instead of using zoom fit by adjusting the y min and max to negative 10 and positive 10. So I'm going to try that now instead. Now, interestingly enough, I didn't actually find an x-intercept, which might be alarming at first, but again, is totally fine. It's normal to run into problems when you're trying to solve something for the first time. Don't let it freak you out. Try and figure out what might be happening. What I think is happening is I think we don't have a large enough x value. I know I should be seeing an x-intercept in there if this problem is even possible. So what I'm going to do is I'm going to change my x max to 150 and see if anything shows up. And by doing so, I see what I want to see. I end up with a graph that looks like this, which might not look like much, but actually shows us everything that we want to see. I want to calculate that x-intercept right there, and in doing so, I can find the initial velocity that solves this problem. So second, calculate option 2 is 0. It wants a left bound, which I know I can put as 0. It wants a right bound, which I know I can put as 150. And then I can hit enter to guess, and it'll take me right to my 0, which is labeled at x equals 100.233, which means the initial velocity that we need to use is 100.233 feet per second.